This is Michelle Van Garrel from the University of Birmingham. So we'd love to hear everything you have to say about AI for mathematics research. Very exciting.
Yeah, I will. Thank you so much. So if you noticed, I don't have admin access to my new computer, so we have to come up with a teamwork in order to share my slides. But I guess that will only add to the fun. Okay, great. So yeah, maybe we can. I'm very happy today to talk a little bit about AI and mathematics. I think there's been a phenomenal development on it, and I'm very happy to show you a bit what's happened. Yeah. So maybe I'll just So maybe I want to start with a personal experience. I think if you had asked me very recently, namely in June of this summer, what I thought about using large language models in order to do mathematics, and here I mean research level mathematics, then maybe my answer would have been that it's not doing so well. It seems a bit like it's trying to pretend. It seems like it's read a lot, and it's trying to kind of imitate what it read. It'd be very good at making connections, but it wouldn't be that great at logic. And then I had this really fantastic thing that happened, which is I obtained early access to Gemini Deep Think. So if you don't know, this is the the most powerful model by Gemini. So thanks go to Honglu, Leslie, and George from Google DeepMind. And so they just give me full access to it in advance, and I was able to play around. This was, yeah. So and today I'm talking a little bit my experiences. So my experience can really be summarized by this image you see, which is I was thoroughly impressed. I was at the time teaching a summer school, and I think my post students, I didn't really take care of them for 3 days because I was just asking every math question that I had stumbled on in the past few years. So I want to tell you a little bit about how this went. Yeah. All right. So the way I'm structuring my talk is I'm going to talk about 3 case studies. I try to make it not too mathematical, and we'll see how well that goes. So the first case study is I want to compare what happened before, meaning what would have a reaction been like in June with what would have a conversation with Deep Think in this case have been afterwards. So of course here this conversation I had this month, just a week ago or something, and I used Gemini Pro, which is the I don't know, the standard or second most advanced model, and I compared it with the performance of Deep Think, so the new one. All right. So the question I asked is, so first I like to say we are both research mathematicians, because then it doesn't then it talks at the right level, because a priori doesn't know how good I am at math, so that helps. So then I gave it two expressions. One expression is A, the other expression is B, and I asked it to prove that A equals B. So that's a very standard mathematical question. So the question was not standard, but that type of format is very standard. And then Gemini Pro gave a mostly correct answer. Not perfectly correct, but it was kind of very good. And then I kind of went very sneaky, and I said, actually, the formula is wrong, which is not true, but I said, and then find the mistakes in your argument. And here then Gemini Pro was like, oh, you're absolutely right. So it wasn't challenging me. And it kind of, I think the answer it gave was, it didn't try to find mistakes where there were not mistakes. It was kind of saying, well, you're right, but actually you didn't read so well, so let me add these extra details. Anyways, yeah. Yeah, and then the next prompt, I asked something completely nonsensical. I asked it to elaborate on some part of the explanation it gave, and I told it to use some theory that has absolutely nothing to do with it. And here Gemini Pro started to hallucinate. Yeah. Anyways, so we can still make it, we can still get it to hallucinate. So now I want to compare this with what Deep Think did. So I asked the same question, and first of all, it gives the correct answer. It was interestingly different answer. And then I did the same challenge, and here the answer was fantastic. So it wrote, as your colleague. I guess it used that language because I said, we're both research mathematicians. And then it said that, that it looked at the proof again, and it found that the proof was correct, and the derivation was sound, etc. And it explains it. So it doesn't like fall for my bluff. So it's in fact it's become much better at kind of logic in the sense of going through arguments, like looking at different cases, etc. And then I tried with my second, like attempt to bluff it, and I asked it to the same question, so to use some theory in that context that doesn't make any sense, and I couldn't bluff it. It was very firm. It's like, well, this is a good idea, but actually it doesn't apply at all. And it really noticed that didn't apply. And so that's just, yeah. So as a conclusion, it really has a it became much better at logic, and it has like a spine. It doesn't worry about challenging you. It doesn't care as much about your feelings as the LLMs of 1 year ago. So that was great. That was great. All right. So maybe I think a framework that's very useful to use is the following framework. So my experiences with LLMs and certainly with Deep Think has been along 3 lines. So this is about mathematics, yeah. So sometimes it would function as an assistant. So I would subdivide some like mathematical questions into different parts, and then ask it to like solve subparts. Sometimes it would like be very good at making connections to other mathematical structures. So that's the thing I attempted to do with this question about fractals, but it realized that there is no connection there. And sometimes it would hallucinate. I mean, that does happen. I think it's just, I think there's this game about, right, like more creativity versus more creativity means more hallucinations. All right, and I think so. Here's is a key message that was always apparent, is that you need to know your mathematics, because if you just trust it blindly, it's not going to work so well. And I think that's the same probably true for like coding, etc. Here I want to maybe mention one of Australia's most famous mathematicians, Terence Tao, who obtained the Fields Medal in maybe 2006. That's like the highest distinction in mathematics. So he wrote he was interviewed for Scientific American about a year ago, and in that interview he talks about a prediction that AI will become a co-pilot for mathematicians. So this fits really in this like LLM as assistant framework, and I recommend, if you're interested, to read this article. Also, Terence Tao has a lot of blog posts. All right. Okay, so this is a math talk, so I have to talk a little bit about mathematics. I promise I didn't try to like I didn't try to like squeeze in some mathematics, but I think it makes sense to say a little bit about mathematics. So I'm going to talk a little bit about these geometric shapes called Calabi-Yau threefolds to convince you that they are interesting. These are pictures that I stole from a Nature paper that came out this year. And in that Nature paper, they really studied certain types of these Calabi-Yau geometries. Here they show it for dimension 1, 2, and 3. If you think that all of them look like dimension 2, you would be right. So this is complex dimension 3, which means real dimension 6. But I know it does not look like real dimension 6, but you can draw this, so you have to like take some slice. But anyways, and then on the right-hand side, there's a thing. There's also a picture from their paper where you have two black holes that meet, and then there's a phenomenon of scattering happening. Yeah. So those are things, so those are things that will appear in the next half an hour or so. So we have, on one hand, we have these geometries, which are these Calabi-Yau geometries. And then on the other hand, we'll have a bit of this scattering. And those are things that you find throughout, that you will find throughout physics, actually. Sorry, throughout physics and modern mathematics, so they are very relevant. Here you can see that Deep Think is better at making images. So this was just a simple request where I ask it, Deep Think, to make a visualization of a very specific Calabi-Yau geometry, and I told it you can use some mathematical software, and it made this absolutely beautiful image, and it gave me explanations of the code of how this of how to make that image. Yeah. Okay, so these Calabi-Yau varieties, or Calabi-Yau n-folds, we're going to restrict mainly to dimension 3, so Calabi-Yau 3-folds. So they're very like big, difficult questions in the topic. One of them is, how many are there? So how many Calabi-Yau 3 are there? What are they? How do you distinguish them? What are their properties? It's very like, all of these are very difficult questions which are largely unknown. So I just try to, I asked. So the images, most of the images you will see, I used the drawing tool of Gemini, and so that's one. Yeah, I used one of them. So, anyways, so then now, if you want to study these Calabi-Yau 3s, one way to study them is by studying their invariance. So you can think about, each of them has some like list of numbers associated to them, and for example, if you want to know the different Calabi-Yau, if two Calabi-Yau 3s are the same, you can check if their numbers are the same. But it's kind of this idea that, well, studying a geometry is very hard, but if we can study like a long list of numbers, then that's easier to study. So on the right-hand side, it's you see an attempt of the drawing tool to like write to show a quantization of Calabi-Yau 3 space into. I don't. The attempt is not so good, but the idea is that one of these invariants happens when you try to quantize your space. So in physics, quantization, you replace a kind of continuous spectrum with some discrete spectrum. In this case, the continuous spectrum is the set of points, and you want to, in your geometry, and you want to replace it by kind of curves that lie inside it. Anyways, that's, counting those is a very hard problem, and then there's other types of problem which is more related to like calculus and integrals, which are easier problem. Yeah, so whenever I write a of x, that's a question that relates to this quantization. When I write b of y, it's a question that relates to integrals. Now on this slide, that you see a mirror. And so one of the like fundamental and deep insights about these Calabi-Yau 3-folds is that they come in mirror pairs. Like they're married to, like they always have like a marriage partner or partner, and they always come like in twos. So meaning that if you have one of them, you know that you have another one, and the way that you notice or you check that they're mirror is that one list of invariants of one, these A invariants, is equal to the B invariants of the others. Yeah. So the A invariant and the B invariants are they're very different invariants, but somehow this like wild and unknown landscape of Calabi-Yau 3-folds is organized by pairs, and these pairs have the like same invariance where you flip the A and the B. So the A invariant of X are equal to the B invariant of Y, and vice versa. We're almost done with the like mathematics, but it's a very fascinating topic, a lot of research. And then there is like a very recent construction which is due to Gross and Siebert, where they figure out how to construct a Y, construct a mirror partner if you're given the initial Calabi-Yau-3. Yeah. So that means we have a very good way of constructing the mirror geometry. And so that helps us to understand this kind of mysterious question, this mysterious landscape of Calabi-Yau folds. But the next very interesting question is, well, is that the correct one? How, is it really the case? Why should we call that the mirror? Yeah. So that would be the question, whether if using this construction, will you really get another Calabi-Yau threefold where the relationship between two will be this equality AX equals BY. Okay. Yeah. All right. So now this is I come to my second case study. So this is a very personal experience where I essentially spent 1 year being completely puzzled, and then when I when I got access to Deep Think, it was extremely helpful at like resolving this puzzle. So let me explain to you. Yeah, this. Okay. So we started. So this was a project. So we take a specific mirror pair X, Y. I'm not going to go into details. So this is, remember, so the X is something, is a Calabi-Yau that we start with, and then the Y is the one we associate using this Gross-Siebert intrinsic mirror construction. Yeah. So everything in the world, everything in the universe tells you that A of X should be equal to B of Y. Yeah. Okay. And so this is a project with collaborators Rudolph and Siebert. And so we look at this very specific example, and we want to determine whether this identity AX equals B of Y holds. And I'm only taking one number to simplify this very specific 1486 divided by 9. Okay? So like everything we know about this field of mirror symmetry tells us that this has to be correct. And if we're able to like prove this using only the geometry of the construction, we will have understood something very deep about mirror symmetry. Okay, all right. So we started about a year ago. We had a conference in Oberwolfach. That's a conference center in Germany. Usually at conferences you meet some acquaintances, some friends. This is a conference you can go hiking. You can do lots of stuff. What we did is every break we go and do we find an empty room with plenty of blackboards, and we do calculations. We fill them with calculations. It's like there's barely enough time to eat. We don't sleep enough. I don't prepare my talk that I gave that week. It was a very chaotic talk. All we do is calculate, filling boards, with endless calculations, and we get the answer 0. I mean, it's like at the end of the week we get the answer 0. It was we worked really hard. We filled so many boards, and we get this very disappointing answer 0, which is not just disappointing because when you do a lot of work you expect to get something other than 0, but it's also disappointing because it's not the number we expect. Yeah. All right, so that's okay. Then but it's actually useful information because we realized that we had to change our approach, right? And then so we changed our approach, we adapted, and then with full enthusiasm we do our calculation again, and this time we get infinity. I mean, okay, I don't know which one's better, 0 or infinity. But probably 0 is better because yeah. But anyways, so we really we at this point the puzzle starts. So we spent all of the fall of a year ago. We question everything we ever did. We're questioning. It's like if you've been trained as a mathematician, you expect that, okay, you get it wrong like 5 times and then you get it right. But here we just kept getting it wrong. We calculate again, and we try different things, and we always get the wrong answer. I should also say that we don't have like the right expertise for this. Yeah, so that's me about a year ago, filling. I don't look that young, but anyways, but filling papers with math and filling papers with more maths and calculating and trying and yeah, anyways. And I certainly did not ask an LLM because at the time I wasn't. It didn't occur to me to do so actually. Right, so in the winter we finally, so sometimes in mathematics you have to like kind of reframe your calculation. So we reframe using it. So we reframe our calculation using some trick, and then we have to use this like result that we find in a textbook from 1923. And using this reframing of the question and the result of the textbook, we finally get the correct answer. And this was really, one like after so much struggling, we're extremely happy. All right, now, but we're not really done because we used a trick, and mathematics loves to use. I mean, we love using tricks in mathematics, but somehow the problem is this trick only works for that examples, and we want to go further. We don't want to like just be able to do one example. We want to be able to do every case, basically, right? And I should say we're missing some kind of key theoretical understanding, and so we're still kind of stuck because we cannot extend the trick, and it's been 1 year already. And so this is when I obtain access to Gemini Deep Think. So instead of preparing my classes for the summer school I'm teaching, I just spend all my time playing around with Deep Think, and it was pretty amazing. So I started with I took one of the things I played around with was this particular question. I gave it, I structured the interaction a bit. So I gave it the initial proof, then I asked it to simplify, and then I asked it later to like generalize in steps and sometimes in new chats, etc. And then what happens next is very interesting. So it so says we go back and forth a lot. I really check everything. I think that's very important. And I also should say that at this point I really understand the problem. It's not like I just try something. I have a very good understanding of the problem because I struggled for 1 year, right? I mean, the amount of time I spent was incredible. So okay, so Deep Think tells me that I should use a Ramanujan master theorem. Now, in mathematics, I have never heard of a theorem called master theorem. So and then it uses the word Ramanujan master theorem. So Ramanujan is this famous Indian mathematician from more than 100 years ago. There was a book about him. There's a movie about him, and then like, was that I couldn't help but wonder, is that like the biggest hallucination that's ever come across? Because like, the name already, Ramanujan master theorem, that can't possibly be right. Anyways, it turns out it was spot on. It was absolutely correct. There is such a thing called Ramanujan master theorem, and Deep Think wrote a complete, rigorous calculation of this invariant by, getting the correct answer, and not just. I only showed you, I only showed you one invariant, but it did it correctly for the whole list of invariants of this example, and also much more general cases. It's just absolutely stunning. I should yes. So and then I should say that in order to prove this identity AX equals BY, you don't just like give it the question. You have to like subdivide it into like the precise statement that you need, or otherwise it will not be able to do. But still, like that precise statement had been evading us for over a year, and it solved it right away. Now, okay, so this was absolutely incredible, extremely helpful for us. And now, but we should also analyze it a bit critically. So maybe, with hindsight, when companies train the LLMs, they give them all the information of the internet, and so it had read all of. So the training of Deep Think involved reading all the publicly available mathematics, research papers, textbooks, the Wikipedia, etc. So it was clear that it developed a understanding that sort of question should be solved with RMT, but it did take a bit of digging to get it to a very precise statement. Now, I should also say that this might have been a question. If I ask the right person, they may have solved it for me. A person that has knowledge in this field called asymptotic analysis, but I wouldn't have known whom to ask. I should also say that if we ask it to compute more complex problems, such as this A of X, then it struggles. It gets some way. It gets some momentum. It says useful things. It can be very helpful to as a helper, but it doesn't really. It doesn't give you a complete proof. Now that some way this could be achieved might be with agentic AI with symbolic math software. So I think this is a very recent development. I haven't tried it in this case, but one could imagine to write some very elaborate markdown file that exactly explains how the proof should go, what the steps are, and then you can have different agents that are trying to prove different subparts, and you have other agents that are checking the already written proof, etc. It might work. I cannot comment on it. Okay, so with this talk is I wrote about. I promised to talk a bit about logic. So in particular, how good is the internal logic of Deep Think? So one thing which is really in favor of Deep Think is that it gave this completely rigorous, fully complete calculation of Py. And I could ask it lots of sub questions, and it would also always achieve this. So Deep Think is so there's a question in the chat. Deep Think is the most advanced model of Gemini, so Google Gemini, most advanced model. Yeah. So you in order to access it, you need either a very expensive subscription or you need to have some friends at Google or DeepMind. Okay, so now I should say, so that was the pro. Now, contra, when you ask it to compute AX, it quickly takes these incorrect shortcuts and gets the wrong answers. And it's still not very good at saying, I don't know. Sometimes it works when you tell it that it should attach some confidence level for arguments, then it works better. It's sometimes I ask it, I say, well, we're both research mathematicians, so we can talk at the same kind of math level, and then I say, we don't have to prove anything to each other. It's okay to say I don't know. It's okay to associate. It's okay to make some kind of. It's okay to write ideas of how a proof might work and associate some confidence level. We don't have to prove anything to each other. This is more of a brainstorming session. So this type of comment can help to distinguish between something that has that is likely a correct proof and something which is probably not rigorous. And then so something I have done and do is once I have a proof by maybe Deep Think, I usually always rewrite it, but then I could just feed it back and ask it to check the proof, and that's kind of helpful. Yeah. All right, and then also maybe it's important to say that the performance varies according to the type of math question. It varies a lot. And some domains it works much better than others, and always I think it's very important that you know your mathematics. Otherwise, yeah, I think that's very important. But and I want to emphasize that I'm not just saying this to make myself feel better, but after 1 year, I mean, I think if I had access to it 1 year earlier, I would have saved a lot of time. But it was still like that year of struggle was quite helpful in the way that you really get to understand the problem. So there were some questions. Maybe I should. Plans for Deep Think to reach. Oh, okay. Yeah. So I cannot say anything about. That's general. Actually, what is GA? General artificial intelligence. Maybe I have nothing to say about that. I have no idea. Yes. So the responses. So I think it really depends on the type of question. So sometimes some types of questions it will give a perfect answer, very rigorous. Those are the type of questions where maybe the proof is very self-contained. It doesn't take a lot of steps, and the statements are very precise, and it works better in general availability. I'm sorry. Anyways, so it depends on the area, and as for API, I don't know if Deep Think has API access, and yes,
it does via cloud, Vertex AI.
So it does. Is the answer it does then? Okay, yeah, Vertex AI, very good. Yeah, and it's probably fairly expensive. Anyways, so yeah, I recommend to try it out. All right, so maybe we go on. And so maybe some comments, why is that happening? So, well, large language models are trained to predict the next word, and they need a lot of training and feedback. Now, in math writing, and here we're really getting to the bottom of it, I think, is some mathematics is written has a certain style of writing, and it's usually written using words. Like we don't write. We use words. So we use a lot of shortcuts. We write like it's clear that is a very typical one, or it's trivial that, or it's obvious, or one can show. It's not because we're arrogant people, though that may sometimes apply. It's more that you cannot give all the details, because if you did give all the details, your papers would be just so long that journals would just not accept them because it's too long. So you have to take these. You have to be very careful about how much details you give, etc. And then usually, when you write, it is clear that it means you know what you're talking about. Like it shouldn't be something you do to skip a proof. And another thing is that every domain has a list of known results and techniques, and that varies by the time era and the time and the domain. Now, if you think about this, so if LLMs are trained to predict the next word, and then the math writing is kind of written in the way I described, then you would really expect that it makes a lot of mistakes, right? Because it will also start to say it is clear that I make some connection, but if it just imitates the writing, it very quickly could make some mistakes. And I think this is what happened a lot in the beginning, when the earlier models came out. And I think this is something where models have become much better at, to some extent. Yeah, but we should never forget the way that we should not forget that it's really, they are trained to predict the next word. They're not trained to understand logic. So how good is mathematical notation? So in mathematics, we usually use LaTeX. So when I talk to it, I write it. I usually write LaTeX, and then so what it writes back, sometimes you can it displays the formulas and the math very nicely, but sometimes it doesn't. But you can always just copy it into a LaTeX editor, and then it will work quite nice. So I think the notation is very good. So I'll get back to some of the questions later, but maybe let's finish this feedback section. So there's also maybe let me say something about, sorry, discussion section. Let me say something about feedback. So, you know, for AI to be very good at recognizing cats in images, it needed a lot of like human input. Like you had an army of people looking at images saying, this is a cat, this is not a cat. And so you kind of need the same thing for mathematics. But of course, you know, if you want to do this at the research level of mathematics, there won't be that many people around, and you know, they will probably not want to spend their weekends like giving feedback to you know, Gemini Deep Think or other models. There is a proof-checking software, which there are several ones. The most famous one would be Lean. But then, so you can imagine that it makes mathematical statements, and then it uses Lean to check if it's correct. But unfortunately, this translation doesn't work so well. So it could be that in I don't know, in some years' time, that translation works really well, and if that happens, it will the math ability will become much better. This is, by the way, one of the reasons. This was one of the like key inputs for models to improve their performance at the like mathematics Olympiads last summer, but not the only one. And then there's also some benchmarks which do rely on human checks. So it's getting better. It's getting it better. All right. Yeah. So there was a question about which areas work well, not well. So combinatorics works really well. Everything where you have like a lot of textbooks will work well. And then the more, so maybe something like symplectic geometry will not work so well. Something more like algebraic will work better. Yeah, I don't have such a good sense on what works, what doesn't work. All right. So AI and logic. So it's getting better, but we still have some ways to go. All right. Now there's one area. So this is my third and final case study for today, at least. So there's one area where it is absolutely brilliant, where it really rocks. And so this is pattern recognition. So we kind of know this, you know, that we know that machine learning is very good at finding some hidden pattern in data, and this also works for mathematics. So one of the first things I did when I got access to Deep Think is I looked at some paper by some friends. It's Lawrence Barrett and Navid Nabijou. This was a paper that was published in a very good math journal, so CREL. So that's the name of the journal. It was published 2022. It appeared, so the preprint appeared 2020. And now, you know, we don't have to go to the details of this formula, but basically this is some identity they came across in their paper. Now, if you look at this identity, you have on the left-hand side, you have a complicated sum. At the bottom, you can see the sum for d equals 3. So you have this like fairly complicated sum, and on the right-hand side, you have a like simple term. So those are well, you can see there are binomial coefficients. You know, you will remember what binomial coefficients are if you like, you know, take a plus b and you raise everything to the power n, or then if you write this out in a polynomial in a and b, then the coefficients will be these binomial coefficients. But anyways, the details are not so important. So I just knew that I just knew that this identity. So my friends had tried to prove it, spent some time on it. They were not able to prove it, so they left it as a conjecture. I know other people have tried to prove it. They didn't succeed at proving it. Now I should also say maybe that's not like the most exciting question in the field, but people have spent some amount of effort trying to prove it and haven't been able to do it. So when I asked Deep Think how to prove it, it proved it right away, and it gave a complete rigorous proof. It was absolutely amazing. And you know, you can see like the thinking, right? And then as you go through the thinking, it's just very beautiful to see like the like mathematical reasoning. It was like correctly distinguishing the cases. It was like telling it was telling me, I think it was me, but maybe it was just telling itself, like how it was like going through the proof, etc. Is absolutely fantastic. And what was really what was kind of stunning and surprising is they used words that I really would not have thought enter like into the argument. Like it used functional equation of generating functions of ternary trees. Like it doesn't matter what that means, but I didn't think that this would be like, I mean, I know what the words mean, but I would never have like, I would never have associated that identity, that early identity, with, you know, functional equations of generating functions of ternary trees. It also used this Lagrange-Bührmann inversion, which actually I did not know at the time. But that's turns out that's a relatively standard thing if you know like analytic combinatorics. So I want to say that, yeah, those are things that will be known to people, to relevant people. So at this point, if you know, they could have, if they had some really good friends in every area of mathematics, they could have asked their good friends to like prove this. But you know, you don't always know you know, all the experts of the fields, and maybe you also don't even know whom to ask. It would have, whoever was going to like seriously prove this was going to spend some significant time commitment, and there's also a bit of an opportunity cost, right? Like you don't know, yeah. By the way, I really wanted to one day give a talk, in mathematical talk, where I can say the words opportunity cost. So I can check this off my bucket list. All right. Now I should emphasize that for Barrett and Nabiju, you know, that formula was not really what their paper is about. Their paper is about something different, and at the end they get this to this formula. So their paper is about, again, I don't want to like say too many math things, but you can see on this image, you can see you have a blue curve and you have this like dotted red line. And what's special about it is, so the blue curve has a degree 3. It's like kind of a little bit twisted. The red line has degree 1, but they only meet in one point. But you can see that if you were to like move the line around a bit, they would meet it in more points. And now among those, so now you can do something very twisted, which is you can like change the equation of the blue curve, so it becomes this, you can see there's this like singularity at the origin, and then you can follow around the like dotted line, and if a dotted line falls into that singularity or meets that singularity, you forget about it. But if you have one that continues to meet the blue curve in one point and never falls into the singularity, then that's one that you will keep. And so basically they were solving this problem of counting these curves that don't fall into the singularity. And then they calculated some specific contributions, so some of these curves, and they found that their calculation gave this expression you saw on the left-hand side of the conjecture. And then they played around a bit with it, and they made this conjecture that tells us what these counts actually should be. Yeah, and so yeah, so that's how they came to that conjecture, and it is one thing that's interesting about this is when you have some complicated expression that is equal to a simple expression, you could ask yourself, well, is there some like deeper reason why I see this, right? Is this formula a manifestation of some deeper geometric phenomenon? Yeah, and the answer to this is yes, as you will see in the next few minutes. But that's very hard to do if you just have the formula and you don't know where to look. Yeah, and so at this point you could do this mental experiment where we can imagine, and this is what we're going to do for the next few slides, we could imagine that they had access to Gemini Deep Think, and they were able to like play around with it and see if they can learn something interesting from their formula. Yeah, and so yes, so the first thing that you could do is, if you remember, the proof had this word ternary tree. So here you can see a ternary tree. So this is a graph. So it has some vertices, and they're like connected by edges. So there's one vertex, which is the root vertex. It's V1. And then you have these like outside vertices, which are the leaves. There are 7 of them. And then you have 3 internal vertices. You can see that at every internal vertex, you have 3 edges coming in. Yeah. So anyways, those are the and if you play around asking Gemini Deep Think about these ternary trees, and sorry, this is a different prompt. So sorry, what I just said was the next slide. So the first thing I did when I asked it is I said, can you generalize the identity? And I did it in 2 different ways. The first way is to just find a generalization, and the second way is I think myself about the generalization, and then I said, well, I want to generalize this formula. Maybe it could work this way. And when I did the latter one, it told me, well, actually, you know, what you propose is not quite correct, but the following one works. And here's a proof. It is absolutely fantastic. It's like it felt like, you know, it's like you're doing mathematics without any effort. Yeah. No. All right. So generalize it easily. And now is the tree prompt. Sorry, I put that slide at the wrong place. So you know, you can ask questions about, well, what are other areas in mathematics where generating functions of trees show up? And then you kind of quickly get to these Kronecker. The name is, you have these like Kronecker quivers, and you have associated invariance to it. Now again, it's not, the details are not so important, but here you can see an image of the three Kronecker quiver. So it's also a graph. We have 2 vertices. We have 3 arrows between them, and then you're looking at representations of this, which are collections of linear maps. And there's like some theory to this. So it's like this is like a advanced way of doing linear algebra. So probably linear algebra will be known to people, but you do it in a more advanced way.
I'm just conscious of timing. Do we want to jump ahead anywhere or have some questions?
Yeah. So okay. Yeah. So absolutely. So let me we just go for it quickly. Thanks for pointing it out. So you can get using this, you quickly get to this generally Kronecker quiver, their invariance, these like scattering diagrams. So remember the black holes colliding, and so those are all connections that you can make just by talking to Deep Think. Now maybe go on, and then you can also ask about auto invariance, and then it really, like, I was very impressed and surprised. It made this connection to these sort of local Gromit invariants of local toric curves. Now, there's really nothing about the problem that suggests this connection. And there's also, these invariants are not like well presented in the physics literature. Like they kind of appear, you know, it's just, they appear as a kind of in passing, but yet it had learned about them. Anyways, so it made these connections, and then you know, if you can work with it, you could basically you could have like proved a lot of results, which we actually did prove in a later paper, which is contained. You see a bit on that side. So yeah. So just to say, so if they had access to that paper at the time, then they may have proven a lot more results, and also for this later paper, it would have saved a lot of time and energy. Yeah. All right. Anyways, so yeah, so we can maybe, yeah, if you could just, yeah. So I'll say a few comments. So there's some benchmarks. Here's one, IM proof bench, very recent. You can take a look at this. Maybe we can move on. Yeah. So there's other areas where AI is used in maths. So there's Jody Williamson at University of Sydney, who does a lot of it. Andre Constantine, my colleague in Birmingham, Mark Lackenby at Oxford. There are these pins, and yeah. So maybe, yeah, you can just move on. So I just wrote a lot of kind of conclusions and things I learned, but we don't really have to, maybe if you can just like move forward. You know, so I can put these slides on my webpage if anyone is interested. So I tried to condense my experiences in some slides. And yeah, so maybe we can just move to the last slide, which is that yeah, it's kind of really exciting and very helpful for productivity. And yeah, we'll see how this will evolve. All right, so maybe we can yeah, move to questions. And oh, there's a really good question about the acceptance level within the math community. Yeah, that's an excellent question. And basically, it depends on who you talk to. So I think that, like, I think that one thing that hasn't happened, it has not been the case that AI has proven like a new result. That has not happened. So, and everyone has had an experience of AI doing, everyone has had an experience of AI hallucinating, right? So then some people will say like, well, I asked it a question and it hallucinated, so clearly it doesn't know logic or mathematics. But that's kind of a wrong conclusion, right? So my personal impression is it's extremely good at making these connections. So if you're working in a math domain where you may want to use different techniques from different areas, it might be very helpful. But anyways, so I think so the acceptance rate really depends on who you talk to. I cannot really give you some numbers, but I think as we're moving forward, it's going to get better and better. And I think that people accept that it's useful for making connections. It's useful for learning new material, etc. So I think the acceptance will go up. Yeah. So maybe yeah. If there are other questions or.
There's a question about a ternary tree, similar classification trees used in machine learning.
Oh yeah, that's a really good question. So it might very well be the case, but I just don't know the machine learning part of it. So trees show up in many different ways. Like it's a very like typical like recursion structure. So the answer might be yes, or it might be no. But clearly, if you know one of them, it will help you understand the other one. Yeah.
Yeah, this is really fascinating, and I think a lot of your takeaways are actually applicable to sort of using LLMs and AI in any field. You know, knowing what the limitations are, knowing what they're trained on, knowing but other fields you can't always prove yes or no whether it's true or not. So this is really insightful.
That's an excellent point. Yes, yeah, that's the advantage of mathematics. And I completely agree. I think it's absolutely applicable, and I think these benchmarks are important for exactly what you just mentioned. Is that how much trust should we give the answer from an LLM? And if you know it's very good at logic and maths, then you can trust it a bit more. And also, I can say that I've had phenomenal experiences using it for like advanced coding tasks. So the summer school I told you about, they would teach, the students were training some reinforcement learning models, and they would use some LLM to get some code running, and then the code would run, but it wouldn't produce the correct the kind of expected training. And then they would give it to me, and I would ask Deep Think to fix the code, and it would do it, and it would work really fantastically. Yeah. So anyways, yeah, so that's yeah, I think I agree with your comment that it's really the most important. I think is you should always understand what's going on, and I think that the lessons from mathematics are applicable to other sciences as well.
Yeah. All right, well, we're at time, but yeah, that was really insightful. So thanks very much, and thanks for joining everyone, and we'll see you again soon.
Yeah, thank you so much. It was a pleasure.